When you tap a video on your phone, a signal races across the globe, pulling data from a computer thousands of miles away. This all happens before you can even blink. How does all that data navigate oceans and underground cables to find its way back to your specific screen in milliseconds? The internet works like a massive digital restaurant, divided strictly into two zones, the dining room and the kitchen. Making sense of the web starts with seeing the wall between these two spaces. Your phone's web browser is like a customer sitting at a table. Because it's the one asking for something, we call it the client. The kitchen half represents the server. These are powerful computers in data centers that spend every second listening for orders and preparing data. The relationship is one-sided. Clients ask and servers answer. This split means your phone doesn't have to cook or store every video on Earth. It just has to know how to order them. That back-and-forth exchange is the request-response cycle, the digital version of placing an order and waiting for the plate to arrive. To find the right kitchen, your phone uses DNS, a global address book that swaps the human name you typed for a specific string of numbers that points directly to a server building on the grid. With the address in hand, your phone packages its request into a specific format and sends it off into the network. Without that lookup, your device would be lost, trying to find a restaurant with no address. To make sure the order is understood, both sides must speak the same language. On the web, that language is HTTP. To see a file, your client uses GET to pull data down from the server. To upload a photo, your device uses a POST command to push data up. Use PUT to update a file, or delete to cancel an order. The kitchen sends back an immediate status code to tell you what happened. A 200 OK means the food is on the way, while a 404 means that item isn't on the menu. By forcing every device on Earth to use these same commands and codes, communication stays predictable and fast. In a real restaurant, you don't talk to the chef directly, you use the waiter. On a server, that role is played by the API. You aren't allowed to wander into the kitchen and grab your own ingredients. That would be a security nightmare. Think about logging into Instagram. Your phone sends a request with your password, but it hits a digital bouncer, the API, first. The API checks who you are before letting that request anywhere near the server's private database. APIs are the gatekeepers. They decide exactly what a client is allowed to ask for and the precise way they have to ask it. Keeping the data in one central place makes everything easier to manage. Engineers can protect the data in one vault and update files for everyone at once. But look what happens when millions try to order at the same time. Traffic jams up, the node overheats, and the server simply crashes. This is a single point of failure. If the power goes out in the kitchen, every single customer in the dining room goes hungry. We trade the independence of our individual devices for the massive efficiency of a central system. The web is a world of clients making requests through APIs and servers sending back responses. How do massive sites like Ticketmaster handle millions of people at once without that central node collapsing? The answer lies with load balancers, hostesses that split the crowd among thousands of different kitchens. We'll see how they handle the rush in the next video.